I'm Wiebke and I'm presenting our work on bias in automated speaker recognition. Speaker recognition is pervasive and increasingly used in high-stakes applications, such as mobile banking, proof-of-life verification of pensioners, and call centers offering public and private customer services. It also adds a security layer to billions of voice-enabled mobile phones and smart speakers. Speaker recognition consists of three core tasks: identification, which determines who spoke; diarization, to separate speakers; and verification, which tests if a speaker is who they claim to be. This last task can be considered as voice-based biometrics. The tasks are closely related and share many aspects of the development process. In this paper, we study bias in speaker recognition with a focus on speaker verification. In our paper, we present an evaluation framework to quantify performance disparities in speaker verification. Using the framework, we evaluate bias in speaker verification. We show that bias exists at every stage of the machine learning development pipeline. Based on our insights, we recommend research directions to address bias in speaker recognition technologies. We designed an empirical bias evaluation framework for speaker verification, which we used together with Suresh and Gutag's framework for understanding sources of harm throughout the machine learning lifecycle, to conduct an empirical and analytical study of group bias in the VoxLab Speaker Recognition Challenge. The VoxLab SRC and its associated datasets are a popular technical competition, and using it as a case study allowed us to systematically analyze bias throughout a prototypical speaker verification development workflow. Our analysis shows that bias exists at every stage of the machine learning development pipeline. Here are the highlights. Historical bias arises in the automated data generation pipeline of the VoxLab 1 dataset, which reinforces popularity bias in search results. Moreover, the pipeline directly transfers bias in face recognition to speaker verification. No surprise then that we found the VoxLab 1 dataset skewed towards males and US nationals. For a benchmark dataset like VoxLab, representation bias is particularly problematic, as it shapes the research culture of the domain and influences future research directions. Measurement bias typically occurs in the process of designing features and labels to use in the prediction problem. In speaker verification, target labels are exactly known, but binary gender and nationality labeling choices in the metadata influence how we consider representation in the dataset and how we design subgroups for evaluating bias. When disaggregating performance curves for male and female speakers of different nationalities, we can observe aggregation bias. Models are likely to perform worse than average for females and better for males. In addition, the aggregate system calibration results in significant operating performance variability across subgroups. Model performance varies across the two models that we evaluated. This is not surprising. However, we found performance disparities across subgroups amplified by a smaller model architecture, indicating that modeling choices such as input feature dimensions and the choice of optimizer can propagate learning bias. Evaluation bias arises in the VoxLab SRC as datasets and metrics present an oversimplified view of model performance. They are insensitive to application context and do not consider emerging applications where speaker verification is used to grant access to downstream services, with false negatives leading to potential harms. Finally, we found deployment bias due to post-processing and due to shifting application contexts, unaccounted application-specific trade-offs between false positives and false negatives, and utterance pairs of varying difficulty grading that do not reflect emerging contexts. Our recommendations thus include strategies for building inclusive evaluation datasets that consider real usage scenarios, and evaluation metrics that consider the consequences of errors. We also highlight learning and engineering interventions that present promising approaches to mitigating bias. Now that you are familiar with the key highlights of our work, I invite you to consult our paper for further details.